Hello, everyone. All right, so this is the very last lesson in Unit 3, so this is called Scatterplots. So I'm sure you guys may have seen Scatterplots before in some context in middle school, or for whatever reason you're looking at them, but you've probably gone over some very bare basics of them. So we're going to really kind of step it up a few notches and really kind of look at some more details. So scatterplots are a statistical tool used to analyze and determine if two variables are what we call related. So we want to see if these variables are going to impact each other. So we are going to be looking for a pattern. So to look for that pattern, we're going to be using what we call the line of best fit. So we're going to be looking for an equation. So that equation is what's going to really help us look for patterns. So as mentioned before in function notation, this is where we're really going to be using interpolation and extrapolation. So inside a given interval, we're going to be looking at interpolation. Outside that given interval or boundary or whatever, we're going to be looking at extrapolating. So there are two types of statistical relationships in scatterplots. There's what we call a causation, which if those two variables are related, then they impact each other. So one impacts the other or one affects the other. So, and then there's what we call an association. So that's if the two are not related and one does not really impact the other. So kind of going off of that, the one most important rule in statistics with correlations is correlation does not imply causation. So think of it this way. In the summer, if it's summer, the sales of ice cream typically goes up. But also with more people being outside, that also could impact, like, for example, this is going way out of context, but it could impact like the number of murders, for example. So if the number of ice creams is increasing and the number of murders is going up, that doesn't necessarily mean the sales in ice creams and the number of murders are necessarily related. So just because a pattern can be derived and created from that relationship, it doesn't necessarily mean that they're actually related. So that's really what we're going to be looking at to see, are these actually related and can a pattern be derived from it? So we're going to be looking and identifying if a relationship represents either a causation or an association. So once again, causation is if they're actually related, meaning one causes the other to be changed, or if they're just being associated. So the number of students and the number of trees, that's an association. They're just being associated. There's no pattern. Okay, so looking at part A, so the amount of flour and the amount of bread baked. So the more bread you want to bake, the more flour you're going to need. So that impacts the other. Nope. So that's going to be what we call a causation. All right, so the number of mailboxes and the number of firemen. Well, the number of mailboxes and the number of firemen don't necessarily impact one another, so that is what we call an association. So the number of students and the number of student desks. So in this case, the more students I have in my classroom, the more student desks I'm going to need. So if I have 20 kids in a room, I'm going to need 20 desks. If I have 30 kids in a room, I'm going to need more desks. So that is going to be a causation, which means those are related. All right, so for part D, so the number of students and the size of the school. Well, if you think of it this way, if I have a school, or if I have 500 students in a building, I don't need that big of a school. But if I have 5,000 students, I need a much larger school. I wouldn't be able to fit that many students in a 500 building or a 500 student building. So that would be a causation. All right, and then the number of cats and the number of dogs. Well, those don't necessarily impact one another, so that would be what we call an association. All right, so then we're gonna look at different types of actual correlations. So if I have what we call a positive correlation, these are positive trends, which means our actual pattern is gonna be going upwards. So it could be kind of flat, it could be pretty steep. As long as it's going upwards, that is what we call a positive correlation. Now, if we have a negative correlation, then it's just a pattern that would be decreasing at some point. So it's just a bunch of data points that are going in the downward direction. So you don't have to put as many points as I am. I'm just somewhat entertained by putting a bunch of points. All right, and then we have what we call no correlation. So that's if we cannot derive a pattern from the data. So it's just, it's not going in an up direction, it's not going in a down direction, it's not really doing anything, it's just there. So that would be no correlation. All right, so now we want to actually identify these as the type of correlation that they are. So in this case, our data is going to be skewing kind of upwards, so this would be a positive correlation. Oh no, or a positive trend. So for the next one here, so our data is kind of skewing downwards, so this would be a negative correlation. And then over here, we have just a bunch of data points. It's not going in any specific direction. We can't really see a full pattern going anywhere, so this would just be no correlation or no trend. Okay, so we're going to get into two specific values. So we have the R value, which is the correlation coefficient, and then we have our R squared value, which is our coefficient of determination. So our R value will determine how strong or how weak a relationship is. So the R value can be anywhere from -1 to +1. So these are just some examples of what could be considered a strong, a negative, or a no correlation, or whatever. So a lot of different data sources will tell you what considers a moderate, what considers a weak, and by all means, like some of these data points, it may be that something else may be better. So what I mean by that is if I consider, say, 0.45, I may consider that a moderate positive, but someone else may consider that a weak positive. So it's really just based on interpretation. It's based on the scenarios, based on the circumstances. It's just based on what you're doing. So this is just kind of a rough interpretation of what you can consider moderate, weak, or strong. So you don't have to actually have those memorized or anything. This is just some extra notes for you. So keep in mind your correlation coefficient. This is going to be your more important value. We care more about the correlation coefficient than we do the correlation of, or coefficient of determination. All right, so our coefficient of determination is going to range from 0 to 1, whereas our correlation coefficient ranges from -1 to +1. So our coefficient of determination, we're literally taking our R value and you literally square it. So the two are kind of hand in hand. So keep in mind, whenever you square a number, you can never have a negative, which is why this is from 0 to 1. You can't have any negatives if you're doing a coefficient of determination. If you got a negative coefficient of determination, you literally broke math, and I have no idea what you did. Please don't break math. So the closer to 1 that the R squared value is, that is a good fit. So you want it to be as close to 1 as possible. If you got it equal to 1, that is like the perfect world scenario. But even if it's just close to 0.1, like if it's like 0.85 or higher, that's a really good fit. Even if it's like 0.7 or higher, that's still a good fit. I would say anything below 0.7 would be not a great fit. But the closer to 0 it is, which would mean it's like you can't have any sort of line of best fit. Like there's no good representation to show the data. So whenever we're doing scatter plots, you can actually derive patterns and do things by hand, or you can do it using technology. So when we're doing it with technology, we're going to be using Desmos. Desmos actually does a really great job of presenting scatter plots. So really the difficult part of this is going to be doing it by hand. All right. So whenever we are doing scatter plots by hand, you want to first draw your line of best fit. So all the steps are up here. So when you draw your line of best fit, you want half the points above and half the points below. So we know this isn't going to be end all be all kind of thing. We know it's not always going to be possible to do that, but you want to get as close as you possibly can. So what I'm going to do is I'm going to draw just a line of best fit. So it doesn't have to be perfect. You want to get something close to it. Let's try to fix this a smidge. Let's put it up a little bit. So I'm going to aim for kind of 2 points to use. So once you draw your line of best fit, then you want to pick 2 points that are on that line, either on the line or super, super, super close to that line. So those are going to be your best points to use. So I'm going to use this point and this point. So I'm going to use, what is it, 6, 80. I can't draw. And then this point over here, I'm going to say is 4, 68. So when you're doing your line of best fit, you may choose different points than I do, and that's completely okay. It doesn't have to be the exact same points that I pick. So once you find those 2 points that you want to use, you're going to use those 2 points to come up with your line of best fit equation. So you want to find the slope and find the y-intercept. So now we're looking for that equation. So between 6, so I'm going to have 4, 68 and 6, 80. So I'm just going to draw these down here for my own reference. So I'm going to find the slope first. So x1, y1, and x2, y2. So I'm going to start by the slope. So this is going to be m equals y2 minus y1 over x2 minus x1. So this is going to be 80 minus 68 over 6 minus 4. So that's going to give us 12 over 2, which gives us a slope of approximately 6. All right, so now that I have that, so now I'm going to start with y equals 6x plus b. So I want to take one of these points. I'm going to take the lower one, and I'm going to plug it in for my x and y. So now I have 68 equals 6 times 4 plus b, and I want to find out what that b value is going to be. So I'm going to multiply. So I have 68 equals 6 times 4, which is 24, plus b. Now I'm going to subtract 24 on both sides. So when you subtract, that's going to give you 44 equals b. So b equals 44. All right, so now I'm going to take my slope and that b value, and now I'm going to write it in slope-intercept form. Also, that line is very crooked and it's bothering me. Okay. So I'm going to have my equation, which is y equals 6x plus 44. So this is our equation. So if you look, we have a y-intercept of 44 that we just derived. If you look at your graph, well, 44 is below 50, so this is a good fit. This is a pretty good equation to use. All right, so kind of some notes over here. So your equation may be different than mine, which is perfectly okay. So if you get a slope of like 5.8 or even 6.2, that's perfectly fine. As long as it's in close proximity to what I got or what someone else got, then you're pretty good. So same thing for your y-intercept. If you got something like 40 or 48 or even like maybe 50, that's fine. Like your equation is going to be different. So just know that like if you're getting something that's like 60 or 70, then that's when it's a little far off. But it shouldn't be too far off. All right, so now I'm going to do the same thing, but for this equation over here. All right, so I'm going to draw a line of best fit. So as you can see, I'm literally just drawing a random arbitrary line. All right, so let's say I use, would be a good point, and let's use this point, this one right here. So this one's kind of a little above. It's all right, it's pretty close. So all these points are actually pretty close to the line, so you should be okay. All right. So let's say that one would be 4, 78. Now let's say this is going to be 7, let's do 66. All right. So guys, if you also notice, I'm approximating these numbers. Like if you say 4, 79 and 4, 77, that's okay. Like if you say 7 comma 65 or 7 comma 68, that's fine. Okay, so I have 4 comma 78 and 7 comma, what was it, 66. All right, so I would say stop here, find the equation. So find the slope, find the y-intercept. Or no, it's fine. So I'm gonna start by finding the slope. So x1, y1, x2, y2. So 66 minus 78 and 7 minus 4. So up here, 66 minus 78 gives you negative 12. 7 minus 4 gives you 3. Simplifies to negative 4. All right, so now I need to do my x comma y. So I'm going to use 7 comma 66, because why not? It doesn't really matter. So I'm going to have y equals negative 4x plus b. And now I want to plug in that xy value. So 7 comma 66. So 66 equals negative 4, that x value of 7, plus b. So I'm going to have 66 equals negative 28 plus b. And now I want to move over that 28. So if I add 28, it's going to give us 94. So our b value is 94. So I'm going to take the slope and the y-intercept, that b value, write my equation. So y equals negative 4x plus 94. So that's my equation. So whenever you get your equation, look back at your graph and see if your graph would actually make logical sense. So usually your b value is going to be your best indicator. So it's 94, which is bigger than 90. So the y-intercept makes good sense. And the slope is negative, which follows a negative trend. So our equation seems like it'd be a good fit. All right, so this is if I want to do it by hand. So I can actually do these using technology. So I'm going to use Desmos. All right, so let's split screen with Desmos. Let me show you my exact screen. Hello, go away. There we go. Okay, so with Desmos, the first thing you want to do is you want to type a table. So up here in the top left, you want to press that plus sign, and you want to go to table. So it's going to prompt you this little screen right here. So I'm going to type in my table exactly how it appears. So 1, then tap over there, 2, and it plots the point on the graph for you. So 3, 5, 4, 7, 6, 9, and 9, 10. So if you look, it plots those points. It's not exactly a linear pattern, but we want to see what our line of best fit would be using technology. So once you get that, then we want to type in the next entry box right below. We want to type in y tilde mx plus b. So this is exactly what you want to type in here. So I'm going to type y, and to get to the tilde, let's expand this as much as we can. I'm going to go to the ABC in the bottom left, and tilde is down here. So I'm going to do a tilde, and then mx plus b. So if you notice, nothing's populating. I forgot to type the ones. How dare I? So y1 tilde mx1 plus b. So now everything's actually generating for you. So if you look, it tells you the coefficient of determination, it tells you the correlation coefficient, and it even tells you the parameters of your equation. So down there where it says parameters, those are just the attributes. So attributes refer to like your slope, your intercepts, and any other relevant data that concerns your equation. So what we just did here is actually what we call a linear regression. So this is a linear regression in Desmos. So what you can do is once you get to this screen, you can literally just copy and paste all that data in here. So your M value is 1, your B value they say is 2, and then they give you your R and your R squared value. So your R value, your correlation coefficient, is 0.9502, and then your R squared value is 0.9029. So you want to round it to 4 decimal places. I know that sounds like a lot, but the more data points that we have, the better. So when you get to upper level math, typically they're going to want like 2 or 3, but especially in like college math, which I know this is a very far stretch. In college math, they want 4 because they want as much relevant data points as possible. So I would say just go ahead and get in the habit of writing 4. All right, so for your equation, you're going to take your M and your B value and just write it in slope-intercept form. So this is literally just y equals x plus b. All right, so for your strength, you want to look at your R value. So if it's 0.9502, that means we have a strong positive value. It falls within this last category here. So this is a strong positive. Let's give more room. All right, and now we want to determine, is the line of best fit a good representation? So that's where we're looking at the R squared value. So because our R squared value is 0.9, that is a really good fit. So yes, R squared is close to 1. So whenever we're looking at the strength, this is looking at the R value. If we're looking to see if it's a good fit, this is the R squared value. All right, so now this is where the interpolation and extrapolation is going to come into play. So I want to know what would be the value of f of 5. So this is plugging in 5. So this would be 5 plus 2, which means f of 5 is equal to 7. Why is that green? There we go. All right, and now we want to find when it's going to be equal to 3. So I'm going to take my equation, so x plus 2, set it equal to 3. So then I'm going to solve. So subtract 2, so x equals 1. All right, so now I want to find f of 15. So if you notice over here, like in your table, f of 15 is not even included in your table. So this is going to be extrapolation. Whereas up here, finding f of 5, that was within the boundaries of the table, so that's interpolation. So here, now I'm going to have 15 plus 2, which in this case, f of 15, which is literally just 17. So some of these equations are going to be pretty simple and straightforward, but some of them are going to be kind of gross and ugly. So now we have f of x equals 8. So taking my equation, set it equal to 8, subtract 2, so x equals 6. All right, so there's that first one. So I will say technology is always going to be your better fit for these just because it eliminates the effect of human error. So if I were to do these up here using technology, it would give me a much more precise line of best fit. So we could approximate it by hand, but technology, hands down, is going to beat us every time. Okay, so I would actually suggest that you try this one on your own. So the good thing about Desmos is what you can do here, now that you've already got the regression down here typed, you've already got this typed, so you can just leave it there. If you want to just edit your table, you can. But one thing that's also really great about this is if you press and hold those green dots right here, if you want, you can actually change the colors, which of course I'm going to change it to purple because duh. You can also change and toggle on the lines. So it'll actually draw lines between those points. So you can kind of see the regressions and how it kind of fluctuates, which we don't need to, but it's just something that's kind of cool because, you know, because I'm a nerd. All right, so I'm gonna turn the lights off. And this is something I really like personally. It's called the drag feature. So I can take, let that go away. So I can take any of these points and I can actually drag it. And as I drag it and adjust it, it will modify my equation. And as I modify the equation over here, all the data updates in real time. So even if I do it over here, like everything will move in real time. And this is just amazing. Like this is actually something I wish I had in college because this would have made my life 20,000 times easier when I was doing statistics. I'm just saying. All right, anyways, so I'm gonna update my table. So 1, 15. Now it's just 3, 10. Now we have 4, 7, 6, 5, and 9, 1. All right, so there's our data. So I'm gonna press and hold. I'm actually gonna take that drag feature off just in case. So here's our data that we want. So I'm gonna move that over a smidge. So you really only need the regression table. You don't even need the table itself. So now that we have MB, R, and R squared, so our M value is -1.688. I'm gonna round up, so that'd be a 2. And our B value is 15.3656. All right, then we have our R value, which is -0.9764. And our R squared value of 0.9534. All right, so I'm going to use that data to write my equation. So my equation in slope-intercept form is -1.6882 plus 15.3656. I forgot my notes. Everything's fine. Excuse me. There we go. That is a terrible X. There we go. Okay, so now I want to know what's the strength of the equation. So if you remember, the strength is your R value. So our strength, we're going to refer to this value. So it's, hello, -0.97. So because it's -0.97, that is a really strong negative correlation. So strong negative. So keep in mind on like assessments or anything like that, whatever we give you, if we're asking for the strength, it's going to be fairly obvious. I'm not going to give you something that's like 0.45 and it's like, is that moderate, is that weak, or is that strong? So I'm going to make it very obvious whether it's going to be strong or weak. I'm not going to give you moderate. I would not do that to you. All right, so now we want to know, is the line of best fit a good fit? So our R squared value up here, 0.95, that's close to 1. So yes, this is a good fit. So 0.9534 is close to 1. Or what you could actually say, you could say R squared is close to 1. Oh, duh, right over there. Okay, so once again, now we're going to be interpolating and extrapolating. So we want to find f of 8. So I'm going to plug in. So this is where you can use your calculator. So over here, that's where I'm going to use Desmos. So if I'm going to plug in, so -1.6882 parentheses 8 and plus 15.3656. So that gives you a value of 1.86. So I recommend doing these in Desmos just because doing these by hand would be absolutely horrible. So 1.86. So now I want to set it equal to 12. Oh Lord, that would be awful. So here's what I would suggest. Get rid of this 8, put an X, and then put 12 equals. So that vertical line, that X value, that's what we want. So X equals 1.994. Or you could literally solve the equation. It's just going to be decimals and it's going to be kind of gross and ugly, but it would still be the same thing. So what I mean by that is you could set up the equation negative 1.6882, that's not a 2, x plus 15.3656 equals 12. So you can subtract 15.3656 on both sides. Okay, so I'm going to do what I call my lazy math. So I'm actually going to write it out, but I'm not actually going to solve it until the very end. So I'm going to write negative 1.6882x equals 12 minus 15.3656. And then I want to divide both sides. Oh my gosh, let me divide. There we go. Negative 1.6882. I don't know why I wrote that like way up there. Negative 1.6882. So x is equal to that whole mess over there. So 12 minus 15.3656 over negative 1.6882. So then you plug that into Desmos or calculator or whatever you want to use. So over here, I'm going to do the division sign so that I open up a fraction. So 12 minus 15.3656. Nope. Nope. There we go. Over negative 1.6882. So it actually gives you a better value when you do that. So we have 1.994 over here on the graph, and over on the Desmos notepad over here, we have 1.9936. So those are both really good answers. So I would take either one. So I do prefer the decimal expansion, so 9936, just because it does give us an extra data point to use, but it's not going to make that big of a difference. So either one is acceptable. All right. So now I want to plug in 2. I should not have done that. Undo. I love the undo button. It's one of the best inventions in the world. So I'm plugging in 2. Let's go over here, get rid of the equal sign. So we have 11.9892. So that's a plug-in, so 11.9892. We plug in 2 for our x value here. And now I want to set it equal to 6. So over here, that 2, change that to an x. Then over here, you can say 6 equals. Oh, that's a y. That should be an x. There we go, 5.548. 5.548.